to prove otherwise, I need strong data. I need my data to pull me away from here. And we can see here that even though this data, that even though the likelihood function here isn't centered on 0, my posterior, still the most probable value is 0. Okay, so even though the shape maybe has slightly gotten this little bump here on the positive side, I'm still using, still 0 is the most probable value in my posterior. And this is good for like regularization, right? If in lasso regression and things of that sort. But really, we can have any shape of a prior. So here's another example, right? Here, what I'm saying, the story I'm telling with this prior is that I don't think that my parameter, that the difference between my means can be very small in magnitude, right? I'm giving a zero prior probability in this range. And what this will look like, it will look like this, right? Any value that got an exactly 0 prior probability remains 0. I can't update that to become more probable. But we can see that this area here, the positive chunk, has become larger. And we can have a prior that looks like this. I don't know what the story is that I'm trying to tell here. I just wanted to make this plot. And if anyone can justify a prior that looks like this, then, I mean, good for you. I mean, that'd be pretty cool. I'd like to see that in a paper. So similar to how we can have strong and weak priors that affect our posterior probability, we can also have strong and weak likelihood functions, which are actually reflect how strong or weak our data is, right? So where stronger data is either a larger sample size or a stronger effect size in our data, this leads to a more specific likelihood function. So we can see, for example, here, that the more data I have, the more narrow this likelihood function becomes, the more it pulls my posterior away from my prior. Okay, so the whole game here is a balancing act in which priors I choose and how much data I have to update my priors, how strong my data is to update my priors, and how strongly it does that. And that's it. That's the basic, in a nutshell, that is what Bayesian statistics is. And we can talk about any parameter in any model you can think of. We can set a prior and a likelihood and a posterior, and it'll work the same way. So why should you even bother switching over to Bayesian statistics? Well, the first thing that Bayes allows you to do is speak in the language of probabilities. This is something that frequentist statistics don't allow us to say. So I can say something like there's a 0.2 probability of the treatment alleviating more than 3 ADHD symptoms. Okay, that's I can't say that with frequentist statistics. I can say what I got in my sample, and I can maybe give a confidence interval around that, but I can't make probabilistic statements of this sort. Or I can say something like there's a 0.85 posterior probability of the reliability of the test being larger than an alpha of 0.8. Okay, so all of these are probabilistic statements about parameters, about effects in my model, in my data, in the world. Another strength of Bayesian statistics is the power of priors. So instead of treating every study like it's the first study ever done, right? Every time we run a little Stroop experiment in our lab, this isn't the first time that we're doing Stroop, right? We know what we expect to see, so why do we keep treating it like it's the first time we're seeing a Stroop effect? So we can actually adjust our priors according to previous findings that we found. Maybe we've changed our the Stroop task a little bit, but we can still maybe somewhat rely on previous results in the Stroop world. And we can also, as we saw, use priors to prevent overfitting. So perform regularization with horseshoe priors or spike and slab priors. These are different type of priors that basically put a large prior probability on a null value in our parameter, which require a lot of data, strong data to pull our posterior away from that. Another strength of Bayes, or really the biggest strength of Bayes, is that it allows us to fit complex model to complex data. By limiting our search space with priors, right? I'm not saying that all probable, right? If I'm not looking at an infinitely large parameter space to search for my parameters in, I'm only limiting myself with priors. I'm saying it's probably around here. We can avoid problems of failed convergence and local maxima or complete separation. And if you've ever come across these terms when running some code or running something in SPSS or however you do your statistics, basically Bayes allows us to circumvent this by using priors to tell our algorithm, tell our model where to search for the result. Additionally, as I said before, with a likelihood function and a prior, we can add endless complexity to our model, even to an extreme case where we have more parameters than observations. I'm not saying that that's something that you should do. You probably should not do that, but it's something that's technically possible. So we can do things like model heteroscedasticity in our model very easily, right? We don't have to use special, complex, robust sandwich type models for this. We just add a prior on an effect on my variance in the model. We can model individual differences in the interclass correlation, easily obtain confidence intervals for random effects, etc. All of these are things that we can do quite easily with Bayes that we either can't at all or are things that are very, very hard to do with maximum likelihood functions or least square, maximum likelihood models or least square models, etc. So now you know what Bayes is and why you should use Bayes. Let's see how Bayesian models are actually fit. Unfortunately, due to time constraints, I will walk you through the process of fitting a model and exploring it. Fitting a model, a Bayesian model, maybe the underside of it is that it takes a long time. It takes longer. Even a simple regression can take several minutes. And I'm sure I see some heads nodding here and laughing that know that sometimes it can, right? I said complexity. That complexity comes with a price, which is usually time. So we will be looking here at a regression model. That is, we have some outcome we're trying to predict. But everything I'm saying here and all the tools I'm demonstrating here can be applied to any Bayesian type of model, a structural equation model, item response theory, signal detection, et cetera, et cetera, et cetera. So all the principles I will be showing are relevant for all of these as well. So our data. Our data is data from 34-year-old children. That is, 4-year-olds, there are 30 of them, who completed Flanker's task. So they have to say what direction the central fish is pointing. So we have a congruent condition where the central fish and the other ones are pointing in the same direction, the incongruent condition where they're pointing in different directions than the central fish, and the neutral condition where I guess the fish are, I don't know, I can't think of a happy situation where fish are pointing up, but okay. We will be examining the interference effect, which is the difference between the incongruent and neutral conditions, and the facilitation effect, which is the difference between the neutral and congruent conditions, while controlling for age. So these kids came into the lab over an extended period of time, and they're not all exactly the same age, so we will be controlling for age in our model. We will be doing all of this in R. So the model fitting, I will be using the BRMS package, which is a Bayesian regression models package for R that uses Stan as its backend. Stan is a probabilistic programming language. So if R is a language for statistics at large, Stan is a language just for probabilities. So you can get really specific, I guess, with how you use your languages. We'll be using the EAMeans package for extracting estimates and computing contrast and looking at slopes. And we will be using the Bayes tester package, which is, as you have stated in the beginning, is one of the packages that I'm a developer of. We'll be using the Bayes tester package for descriptives and inferential statistics. And all the beautiful plots that you are going to see in this presentation have been made with a mix of all of these really excellent packages. So let's start. We'll be using the BRM function, The syntax for building a model with BRM is very similar to fitting any type of model if you've done so in R before. So we have, we're saying here that response time is modeled by congruency, which is a factor, and a fixed effect of age in months, right? And if you fit mixed models in R before, then you also would recognize this. We're saying that there are random effects for congruency nested within each participant. And our data comes from a data frame called child flanker. This is essentially a repeated measures on COVA. So these, if you run a repeated measure on COVA, you should get very similar results to what we will get here. I will just note that for congruency, I am using a type of dummy coding called orthonormal dummy coding. This is important, but I don't have time to get into this. I encourage you to either blindly do this also or read more about it here. It's very important, especially with how these models use priors on factors. Speaking of priors, this is how I set priors in BRM. So I will be quite conservative in the type of prior I use. I'm going to use a prior that's shaped like a T distribution with 3 degrees of freedom, which I will scale, right? So T is pretty narrow. It's around 1. I'll scale it to whichever I need. The benefit of using a T distribution with 3 degrees of freedom is that my scaling factor also defines the 60% central probability of my prior. So if I scale my T distribution by 2, I'm saying that there's a prior probability that the coefficient or that the parameter is between of 60%, that it is between -2 and +2. If I scale it to 4, I'm saying there's a prior probability of 60% that it's between -4 and +4. So it's just an easy way to kind of think about what we're saying, right? I'm also saying that there's 20% probability that it's larger than 4, and that it's another 20 that it's smaller than -4. So that's just the way that I've chosen here. There are different shapes of priors, as I've shown before. You can use wider priors or more narrow priors, etc. So for the fixed effect of congruency, in adults, the flanker effect is usually somewhere between 20 and 50 milliseconds. But here we're talking about 4-year-olds. So I'm going to argue, right, I have to justify my priors. I'm going to argue that the differences can be expected to be around 100 milliseconds. Okay, so I'm going to be using a scaling factor of 100, which means that I'm assigning a prior probability of 60%, that any difference between any of the 3 groups is between -100 and +100 milliseconds. But I'm also allowing for more extreme results than that, right? But like, it's not very probable that they're very extreme, right? I'm not using a very wide prior here. I'm using relatively narrow prior. For age, right? So all of that was this, a T distribution centered around 0, scaled by 100. For age, I have no idea what to expect. I don't know what the effect of age is on reaction times. So I will use a very weakly informed prior scaled to 1,000. All right, so I'm saying that there's a 60% prior probability that the effect of age is a change of about a second, or an increase in a second, or a decrease in a second per month. Okay, but also these can be more extreme. I'm still allowing for more extreme probabilities. That's why this is a very, very wide prior to use. Just some notes. By default, BRMS assigns flat priors to all fixed effects, which is okay if that's what you want, right? But those aren't objective. Just have to remember that those aren't objective priors. I also say that we can have set more other priors in this model. For example, I can set a prior on my error variance, on the random effects variance, and etc. You can see all of that using the get prior function from BRMS. I've chosen just to focus here on the fixed effects in this model. Okay, and finally, my likelihood function is a Gaussian likelihood function. That is, I'm saying that reaction times are conditionally normally distributed, which is a basic boring linear regression. And we can argue if that's appropriate here or not, or we can objectively check it if really they do are normally distributed. Okay, so after we run all of this code, we get a model. And on this model, we need to perform some basic prior and posterior checks. These checks just make sure that our model is very generally reasonable and that we've done a good job of sampling from the posterior. Unfortunately, that's a whole other topic for another time. But I've done this for this model, and you can check that out here in the full analysis script in this link. Okay. So let's explore the model after we fit this model. Okay, so the first thing we want to do is we want to look at the congruency effect, or the congruency means. I will be using the EM_means package. For that, if you're not familiar with EM_means, what I'm doing here is I'm saying from the model mFlanker, give me the means as they are according to the effect of congruency. So that's what I'm doing here. Unlike frequent test estimation methods, such as least squares or maximum likelihood, which produce a single point estimate for every parameter in the model, in Bayesian models, we don't have a point estimate. We actually have a whole posterior that we can use. So when we want to present results, one option is to just show the complete posterior of the means. Okay, so what we can see here, these are two different ways of showing the posterior distribution. We can see here that the incongruent condition has, right, the whole posterior seems to be shifted upwards compared to the neutral and congruent conditions, which seem to be pretty close together. So this is one option of presenting results. But if we just did this, then all of our papers would just be all these huge plots of posterior distributions. So what we can do is we can summarize our posterior distributions. We can use a representative value, which isn't a point estimate. It's just some value that we're choosing to be the most representative. Some options are the median. Okay, that is the value above which 50% of my posterior lies and under. Another option is the mean. And another option is the maxima posteriori point, which is the value that is most probable in my posterior distribution. The most common of these is to use the median, and that is what I will be using here. And we can also show uncertainty in my posterior distribution using a credible interval, which is not a confidence interval. It's a credible interval. It's still spelled CI, which is just very confusing. Here, too, we have several options. The first option is the highest density interval, which is the interval that has the most probable values within it. And we have the equal tail interval, which is more familiar to people transitioning from frequent statistics, where we just, right, we slice equal tails off of our posterior. So I can say I'm cutting the 2% highest values and the 2% lowest values, and now I have a 96 credible interval between these ranges. We can do that with the describe posterior function from Bayes tester. So I'm giving it our result here from EM_means. I'm telling it that the centrality parameter, the centrality measure I want is the median. I'm telling it that the credible interval method I want is the HDI, the highest density interval, which is the most popular one. And the level of credible interval that I want, I'm using here 89%. Why 89%? Well, why 95? In frequent statistics, it's very common to just always use an alpha of 5%, or it's complementary of a 95% confidence interval. In the Bayesian world, you'll see varying values, right? Some people use 99%, some people use 90, as a kind of what started off as a bit of a joke where we shouldn't use whatever, just a single value everyone. So some people started using 89%, and that has caught on, which is a bit of ironic. So this is the result we get. So for example, we can see that for the incongruent, the mean of the incongruent condition, the most probable values are between 1.4 seconds and 1.7 seconds, with the median value of 1.6 seconds, and et cetera. The same thing we can see for the neutral and congruent conditions. So that is that. Okay, finally, evaluating evidence and making decisions using Bayesian statistics. That's what we all came here for. I will just say up front that we're limiting our discussion to evaluating evidence of single estimates or parameters, that is, of a single mean, of a slope, a contrast, etc. There are other methods for evaluating evidence for multiple parameters, but maybe, I don't know, maybe next year we'll see what happens. Let's first create our contrast. So again, I'm using the EM_means package for that. I'm using a contrast for my interference effect and for my facilitation effect. And what we can see here, I'm again using describe posterior from Bayes tester. We can see that the interference effect ranges between 48 milliseconds and 285 milliseconds with a median value of 166. And we can see that the facilitation effect ranges from minus 154 milliseconds to plus 35 milliseconds with a median of 56 milliseconds. Now, anyone who's maybe familiar at looking at confidence interval and seeing if the zero falls within and rejecting the null according to that, you might be getting some kind of sense of maybe what's going on here. But let's explore that using the Bayesian way. So I'll be showing several indices that we can use for making decisions. The first one is the probability of direction. The probability of direction is the maximal probability of the estimate being strictly directional, that is, being strictly positive or negative. It generally ranges from 50%, where there's no preference at all, right? There's 50% of it being positive, 50% of it being negative, to 100%, where basically the whole posterior is either positive or negative. We can get the probability of direction with the p-direction function, again, from Bayes tester. And we can see that for the interference effect, there's a probability of direction of 98%. And for the facilitation effect, there is a probability of direction of 83%, right? So if we're looking at the posterior of the interference effect, we can see that only a very small amount of it lies right on the other side of the zero. Whereas for the facilitation effect, we can see that indeed most of it is negative, but there still is quite a big chunk here that is positive. Okay, so it's less strictly directional than the interference effect. The pros for using the probability of direction are that it's easier to understand, right? It's relatively straightforward. It also resembles the p-value from frequentist statistics. What is the p-value? What is the p-value testing? It's testing whether what I got in my sample, right, my estimate, is it different from zero? What does it mean to be different from zero? It means being positive or negative, right? That's actually what we're saying. We're saying that the effect has some positive or negative sign. And indeed, in many, many practical implications, there's a -1 correlation, almost a -1 correlation between the probability of direction and the p-value. So if I were to compute a p-value for these contrasts, they would be very similar, but in the opposite direction, right? So high probability of direction is associated with a low p-value, and on the other way around. This also leads us to the con of using the probability of direction, that just like p-values, low probability of directions cannot be used to support the null, right? So from this very high probability of direction, it's quite clear that this isn't a null effect going on here. But from here, we're not as clear, right? I mean, this is still giving us some information about our posterior, but it's not as clear. It's not as clear. And we can't actually use the probability of direction to support the null for that reason. Another measure is called the p-map, which is not a probability. It is a density ratio between the null value and the maximum a posteriori value, right? The most probable value in a posterior distribution. The values range between 1, where the null is the most probable value, and very, very, very close to 0, where the most probable value is many, many times more probable than the null. We can get this measure using the p-map function, where we find that the interference effect has a p-map of 0.08, right? We can see here that the maxima posteriori value is more than 10 times more probable than the null value, which is what we have this little dot here. Whereas the facilitation effect has a maxima posteriori value of 0.65, where the most probable value isn't even twice as probable as the null value. So the pros for this are, again, it's familiar. It's closely related to likelihood ratio tests. which are used in maximum likelihood estimation and inferences. And because of that, it's also closely related to the p-value. But again, because of that, this similarity, a high p-map cannot be used to support the null, right? So again, here, a low p-map, it's quite clear that, that my posterior is not anywhere close to the 0. But from here, right, it's unclear. Maybe it's close to the 0. Maybe it's just very wide. It's not very indicative, not very informative in itself. Our next measure is called the probability of rope. The probability of rope is the probability that our estimate is basically null. What do I mean by basically null? Well, first, we need to define a region of practical equivalence, a rope. This is a range of effects or of parameter values that for any practical purpose, we consider them to be just the same as no effect at all. Okay, so for example, for the congruency effects, I will be defining any effect that is smaller in magnitude than 30 milliseconds to be considered just as good as no effect at all. So my rope is between -30 and +30. And similar to how I have to justify my priors, I also have to justify my rope. Okay, so I can't just use whichever values I want. They have to be reasonable. Who decides what reasonable is? I guess reviewer 2 decides that. But here, this is what I will be using, right? I can't just use, let's say, that any effect size smaller than Cohen's d between -2 and +2 is equal to null. That's not a reasonable statement to make. So we have to use the same careness for defining our rope as we do when using and defining our priors. I'll just say that we can have one-sided rope. For example, any effect that is smaller than 30 milliseconds, I will consider to be just as good as no effect at all, right? We can think in treatment, in the context of treatment. If my treatment is bad, I don't necessarily, I'm not interested in how bad it is, right? As long as it's not beneficial, I would consider it bad. So this is something that's possible. I won't be doing that here. So what are we actually asking? We're asking how much of the posterior falls within the region of practical equivalence. Or more often, we're asking how much of the most probable values, those in the high density interval, fall within the rope. We can do that with the rope function from Bayes tester. So I'm defining my range here between -30 and +30. And I'm using the 89% HDI. And what we get is that for the interference effect, 0%, or there's a 0 probability of the most probable values being null, right? We can see that here. Our HDI is the shaded blue area right here. And we can see that none of it fall within the rope, which is the red rectangle here. Whereas for the facilitation effect, there's about a 30%, excuse me, there's about a 30% posterior probability of my effect being null. Now, that's not very strong, okay? That's not very conclusive. We want this to be as close to 1 or as close to 0 as possible, right? Either the whole posterior is within the rope, or none of the posterior is within the rope. But still, we are able to give some support to the null, right? We're at least saying that the null has some non-trivial posterior probability. And if you've ever heard people talk about that Bayes is good because it can be used with small samples, this is what they mean. Okay, unlike with frequentist methods, where small samples and non-significant results kind of leave you with nothing to say, Bayes allows you to at least say something. Weak as it may be, at least we can say something, right? We're able to give here some support to the null. Of course, we're also able to say that there is about a 70% posterior probability that it's not null. Okay, and then we can investigate how big is this, are the non-null results, etc. But we're still able to make some probabilistic statement. Okay, no matter how strong it is, we're still able to say something. Excuse me. Okay, so the probability of direction, the p-map, and the rope are all posterior-based methods. That is, they inform us about the accumulated information in the priors and our data, right? So the posterior is always a mix between the priors and our data. But often we're interested in what has been learned in the current study from the current data. For example, it's clear by now that there is an interference effect in flankers test, but which values of this effect are supported or contradicted by our current data, right? What has our data added to this prior knowledge? Or maybe our data supports the null for some reason, right? And then what can be learned from that? So to answer this question, we can compare the prior to the posterior, right? Any difference between the prior and the posterior is actually what has been taught, what we learned from our data. And we can see which values became more or less probable in the change between the prior and the posterior. So this would look something like this. If in blue here, we have the prior, and the green is the posterior, so the areas in orange here are values that our data has indicated are less probable, right? We've moved away from those values, whereas values here in the red, we can see that this is where our data taught us that these values are more probable. Okay, so we're actually asking questions about what our data has taught us, which values are supported or contradicted by our data. So for example, I can now compare two hypotheses. I can ask, right, how supported is the hypothesis that my parameter is small, that it's between -3 and +3. Okay, so I can see that in this range, some of the values gained support, others did not. I can also ask, right, how does my data support the hypothesis that my parameter is positive, right? So again, I can see that for all positive values, some positive values gained support, some lost support, and I can actually compare these two hypotheses. I can ask which of these two hypotheses is more supported by our data. An index that answers that type of question is a Bayes factor. It quantifies how the prior was updated to the posterior, and it compares two hypotheses. Essentially, any measure that quantifies these two things is a Bayes factor. So you may have used Bayes factors to compare between models. Also, those Bayes factors have these properties. So there are many, many different types of Bayes factors because there are many, many different types of questions that we can ask that have these properties. We will be looking here at two types of Bayes factors. For technical reasons, we need an additional model to the model that we just fit. We need a model that is just our priors. Essentially, we want to unupdate our model, right? Our model has the posteriors, so we want to unupdate that. We can do that with the unupdate function to get a model that represents just our priors. This is just for technical reasons, but it's essential that we do this. So the first Bayes factor we will be looking at is called the null interval Bayes factor. It is an extension of the rope, which we saw before. And it answers the question, how has the relative probability of the effect being practically null changed? Does our data support or contradict the effect being null? So in our example, we can formulate our two competing hypotheses in such a way where the null hypothesis is that our effect is in the rope, right? It is between -30 and +30. And our alternative hypothesis is that the effect is outside of the rope. That is, it's either smaller than 30 or it is larger than 30. We can do that with the Bayes factor parameters function from Bayes tester. So we're giving it our contrasts. We have to supply our prior model. That's why we made it before. And we're going to specify that the null is a range between -30 and +30. And what we get is two Bayes factors, one for each of our effects. So for the interference effect, we have a Bayes factor of 6. What does a Bayes factor of 6 mean? It means that non-null values, values outside of our rope, are supported 6 times more than values inside of the rope. Visually, we can see here that the rope lost, right? It lost its probability from the prior to the posterior. Essentially, if the rope has become less probable, then values outside of the rope have become more probable. And the Bayes factor quantifies this. It tells us that values outside of the rope are 6 times more supported than values inside of the rope. For the facilitation effect, however, we see a base factor of 0.5. So a base factor of 1 means that nothing has been learned, or no hypothesis is preferable. So a base factor smaller than 1 means that the null has gained some support more than non-null values. And we can again see that here in the plot, that values within the rope, which is again this red, the shaded red area, have become more probable in the posterior, which means that relatively values outside of the rope have become less probable. And we can, in fact, say that the null is supported twice as more as non-null values. So that's what we get here. That's what I said. So this is one type of base factor. Another type of base factor is the point null base factor. So we can think of the point null base factor as the null interval base factor, where we're making our rope extremely, extremely narrow until it only encompasses a single point, just the exact 0, just exactly the null. This answers a similar question. How has the probability of the null value changed? Does our data support or contradict the effect being null? This base factor is also called the Savage-Dickey density ratio. And it is analogous to a base factor comparing 2 nested models. Okay, so if you've compared a model with some parameter to a model without a parameter and gotten a base factor, this base factor is analogous to that. So they should be mostly interchangeable between them. And this one is a lot easier to compute. So that's an advantage for this. Again, we're comparing 2 hypotheses. All right, we always need to remember that base factors are always comparing between 2 hypotheses. Our hypotheses here are, the null hypothesis is that our effect is exactly 0. And the alternative hypothesis is that the effect is not 0. Okay, so that the effect is either positive or it is negative. To get this, we basically run the same code as before, just that instead of null being arranged, now null is just a point. So I'm saying that null is 0. And we get here that the interference effect has a base factor of 5.9. That is that the null has become relatively less probable. We can see that here. That non-null values have almost 6 times more support than the null value, right? Now it's just one value. Whereas for the facilitation effect, we have a base factor of 0.59. We can see again that the null value became more probable. And this is again what I said. I will note that in this case, both these types of base factors, right? Also the point null and the null range base factor gave us very similar results, 5.9 versus 6. 0.59 versus 0.51. But this doesn't have to be the case, right? This depends on how we define our rope, how strong our data is, what our posterior looks like, etc. So these don't always have to be the case. They will tend to be congruent with one another, but not to the same degree, at least. As I said, there are other types of base factors. So basically any hypothesis that we can define as a range of values or some combination of values can be set as a base factor. So for example, we can use directional values of the null interval or the point null base factor. So I can have a null hypothesis that my effect is between -30 and +30, and an alternative hypothesis that the effect is larger than 30. So between +30 and infinity, we can have a base factor for dividing hypotheses, where I'm comparing one hypothesis as that the effect is negative compared to another hypothesis that the effect is positive, and more and more and more. There are many, many different types of base factors, as I said, and you can read more about them in this little link right here. Oh, age, right. We also had a parameter of age in our model. So for covariates, we can present our posterior distribution, just like we did for the means, right? Just show the posterior distribution of slopes. But an alternative way to show is to sample some slopes and just plot them out. And we can get a plot like this called a trace plot. And we can get some kind of sense of what the posterior looks like from this, right? We can see that most of the slopes seem to be positive, not very strongly positive. We see that there is a lot of variation, right? So this means that our posterior is relatively wide. And we do see that there are some negative slopes as well, right? So if there are some negative slopes, we can already say, even without checking, that the probability of direction isn't 100, right? So they're not all positive and they're not all negative. Here too, of course, we can summarize our posterior distribution. So again, using the median and the 89% HDI. So we're saying that the slope, the most probable values of the slope are between minus 47 milliseconds per month, right? It's a slope, to 100 milliseconds per month with the median value of 22 milliseconds. And we can also just plot that out like regular, right? Having a single slope with a credible interval around it. Let's look at the probability of direction and the P-map. So the probability of direction is 67%, right? 67%, we saw before, 67% of our posterior distribution is positive, but that also means that about 30% is negative, okay? And for the P-map, we get a P-map of 0.8, which means that the most probable value isn't even twice as probable as the null value, okay? So once again, these aren't very decisive, right? We can't use these to support the null, but we can use the rope. So let's use the rope. For the rope, I'm going to define that any effect that's smaller than a change of half a second per year, right? That for every year that I get older, I either become faster or slower by half a second, which is about 40 milliseconds a month, is practically equivalent to 0. You may disagree with me. Maybe you define what effects interest you in a different way, but that is how I'm defining my rope here. And what we get is that 63% of the most probable values are null values, according to how I define the rope. Okay, so this is, again, this isn't super convincing, but it's very, very indicative, right? It's saying that null values are more probable in the posterior than non-null values. It's very, very suggestive. Let's look at the Bayes factor. So I'll be using here a point null Bayes factor. And we see we get here a Bayes factor of 0.052, right? That is, what this is saying actually, that our data has supported the null 20 times more than it supports non-null values. Okay, so, I wrote here rope. This should not be inside rope. This is just the null value because we're talking about the point. But we need to remember that the Bayes factor measures change from the prior to the posterior. Okay, and what prior was it that we used here? We used a very, very wide prior. Okay, before we've seen any data, we've given the null value a very, very low probability of being true, right? Because it's so dispersed. So is it really surprising that in the posterior, the null has become more probable? It shouldn't be very surprising. And really, with any wide enough prior, our Bayes factor will always favor the point null or the rope. So it's very important to not compute Bayes factors if we have uninformative priors. That's the take-home message from this slide, at least. So of all of that, what do we actually recommend? So in a paper we published in 2019, where we simulated how all these indices behave regarding to effect size, sample size, and how are they related to p-values, we recommend reporting the probability of direction, which is easy to understand and easy to mentally translate into p-value for novice readers. And we recommend the probability of rope, which provides information about the practical equivalence of our effect and also allows for accepting the null. And if informed priors were used, we also recommend reporting a Bayes factor, either instead or in addition to the probability of rope, which provides information about hypotheses and how they are supported or contradicted by the data. So what do you now know? You now know what a Bayesian model is. You know a little bit what Bayes can do for you that other model types can't. You've gotten a taste of how to fit a model with the BRMS package. and a little bit of the richness of inferences techniques that can be made with Bayesian statistics. So basically any transformation or estimate or measure that you can get from the posterior is a valid one, okay? I've just shown you the most popular and most common ones. For anyone who wants to read a bit more about the topic, here's some suggested reading. This is our paper with the simulations that I talked about before. These two are really good introductory sources to Bayesian statistics. I highly recommend them. And also some really, really good books about statistics in general and Bayesian modeling more specifically. And that's it. I was Mattan. You can follow me on Twitter, see my stuff on GitHub, or read in my blog. The Bayes tester package is part of the EasyStats project. So I'd like to thank Dominic, Daniel, and Indrajit for their work within this ecosystem. And that's it. Any questions? I see that Naomi asked if I can write which versions of packages I've used. Yes, I will. I'll add that after the talk to the slides.
I have a question about like using the stand versus using JAX, because I use Krushka's book and I use JAX, and I know it takes a lot of time like to build the model string within Krushka, and I saw like that what you used was like very simple lines of code in R. So I was wondering if there is any advantage for using the JAX over stan or otherwise.
Well, I don't have any experience with JAGs. I would imagine that if you're purely writing like the actual code, right, then they both would take an excruciatingly long amount of time. But really, the advantage of Stan is that it has this port into R. So the BRMS package. There's also a B-Lavan package for structural equation modeling. There's also RStan ARM, which is kind of like a stripped down version of the BRMS package. All of these have kind of like either have precompiled Stan code, or they translate the kind of regular R syntax of a formula into Stan code for you. So that saves a lot of work. I personally don't know any JAGs, WinBugs, Stan. I don't know how to write any of that. That's too scary for me.
Yeah, I can understand. Thank you.
Nitzan.
Hey, Mattan, thank you so much. I mean, first of all, that's just an excellent workshop and so much needed, and you explain things so clearly. So thank you for that. I wanted to ask two brief questions. So first of all, I don't know, maybe other people as well. I didn't get exactly why an uninformative prior is less recommended. I understand that it will favor the null, but isn't that the case that we would actually want to be able to show that under most strict conditions, we actually get a Bayes factor for H1? And the second very technical question is, many students use JASP, and I was wondering whether you can tell us, if you know, what kind of Bayes factor is computed there, and is there any limitation we should consider?
Okay, so for your first question, I'm just going to go back to, you were talking about this?
Yes, exactly.
Okay, so we can see here that even if I shifted this prior a bit to the right here, okay, where it wasn't, right, in this case, it's like smack centered over the null. But basically, if my prior was flat enough, no matter where my posterior was, there would be some gain in probability in the null value, right? It couldn't be as equally flat. So the null would always gain some probability from the prior to the posterior, which means it gains some support. And if the null gains support, then relatively, on average, all the non-null values have lost support.
Okay.
So that's that. About JASP, the Bayes factor that is computed in JASP is a Bayes factor for comparing between models. It's based on marginal likelihoods, which I didn't talk about here at all. But as I said, if I would go back to here, right? This type of Bayes factor where we look at the prior and posterior and compare just to a point null is analogous to a Bayes factor comparing nested models. So if you were to compute in JASP or anywhere else a Bayes factor between a model with some parameter compared to a model without that parameter, they would be nested, and that Bayes factor would be very, very close to a Bayes factor that you would get with this method. I will say that in JASP, they have a very specific family of priors on all of their effects. So here I was able to define, right, very flexibly define my priors on the scale of my measurement. In JASP, all the priors are defined on a scale of the error variance, which is kind of like Cohen's d, which maybe makes sense in ANOVA, but not so much in regression. We're not usually taught to think like that. Yeah, I don't know what else I can say about JASP.
That's super helpful. Thank you so much. Really,
Sure.
that's very helpful.
Mattan, I'd be glad to ask. Can you please explain again what's the difference between the HDI credible interval and the equal-tailed one?
Yeah, so the HDI, essentially okay, so I'll start with the equal tail one because that's like the easier one to explain. The equal tail one says I'm just going to cut off equal probabilities of my tail, of different tails, right? So I'm going to cut off, let's say, 5% of the highest values and 5% of the lowest values, and I'm left with a 90% equal tail credible interval. That's how that algorithm works. For the high density interval, I'm actually asking what is the narrowest width of an interval that contains 90% of the posterior. So if my posterior is like bell curved and symmetrical, generally those two will give the same result. But if I have some skewness, then the HDI will be more narrow, will be more specific. That's why people use that more often.
Thank you.
Hi, Mattan.
Hi, David.
Hi. Can you repeat about the explanation regarding the determining prior? This is the most
yeah, I don't think I'll be too helpful there because
difficult point.
Yeah, you have to justify. You're talking about justifying your prior?
Yes. This is the basic process that I decided how.
Right. So there are many different ways to do that. There's like let's say in JASP, they wrote, the developing team there of Richard Morey and Jeff Rauter. They wrote a bunch of papers justifying the default priors that they use in the Bayes factor package, which is used in JASP. So that's kind of like just a one size almost fits all kind of situation. But you can go about it in other ways. There's a really good paper, maybe I'll add it to the reading list and then you can access it later, where they kind of give a bunch of rules of thumb how to justify different types of priors for different types of parameters. What I did here is I kind of just Google Scholared flankers task, looked at some table twos to see the difference, and I used that as a basis for my prior.
Okay, because I saw that a lot of people just skip it in the papers.
Yes. A lot of people either skip it because they don't know that it's important to report it, or because they just say we use JASP, and then everyone kind of knows what prior they, or doesn't know, or supposed to know what priors they use there, essentially. But yes, it's an extremely important thing to choose, even if we're not talking about Bayes factors, right? We saw that using the different priors does affect how our posterior looks like, what we can learn from our data.
Can I ask?
Yeah.
When you do Bayesian analysis, is there any advantage to pre-registering your priors or your intent of how to look at the data, or since you can look at it in multiple ways, it doesn't matter if you've looked at it 10 times, pre-registration has no added value?
Pre-registration. Wow, there's a whole thing going on Twitter today about that. So I'm not going to talk about pre-registration. Let me maybe ask about multiple comparisons. Is that kind of that? There's a
well,
really...
not exactly. Well, yeah, answer about that as well. But
I'll answer about multiple
but
comparisons.
without saying pre-registration. Let's say I've justified my prior in a way that makes sense to me. Now reviewers say it doesn't make any sense. And so I just show both priors, that the results with both priors in the paper, and let
I mean, you can
or I just take whatever the reviewers say because it doesn't matter that I also did another test.
Well, if you you can look at different at your results under different prior conditions, and that's called a prior robustness check. You're actually seeing if how your results change by how you change your prior, which is something that, if you need to do, if you want to do, you can totally do. You can also aggregate all the results, right? So I can just kind of take all the posteriors and kind of chain them together to have like this mega posterior distribution from all the models with all the priors and kind of like this mixed prior kind of situation. I don't know what to say about in the context of pre-registration, but like I guess anything that would be true for pre-registration for non-Bayesian statistics would be true here, right? If you pre-register that you're gonna fit a model in some way, and then a reviewer says that you should have done it in a different way, then I mean it will be just as, whatever the answer is for that question, it's the answer for this question.
Is there, I know in JASP, I did that once, there's a robustness, just you just tick that.
Yeah.
Kind of gives you the, at what point of a prior your results would change in a way that would be interesting.
That's not available yet, but we are working on adding that to the base tester package to have a function that does that.
So you would just run multiple models with different priors and then see at what point, report at what point this changes in a way.
I will say that like generally base factors are more sensitive to changes in the prior, right? For the reasons that we saw before. For the posterior, as long as you're using something that's even like vaguely reasonable, you'll get roughly the same results. But yeah, you can totally do that. About multiple comparisons, there's a paper by Andrew Gelman that argues that using priors actually negates any issues that could be with multiple comparisons. So I didn't talk about alpha or any error type or anything like that. That's not the realm that we're in. So that's not something we need to worry about. There is some work from the team over at JASP, Tim, I don't remember his surname, that are talking about kind of like adjusting our priors for multiple comparisons, but that's like a whole other thing. I know that in most cases people don't do any adjustments because we're talking directly about the posterior. We're not like making a dichotomous decision, so to speak. So there's less of a need for that.
I can't see if other people are pointing, so if they are, I can wait. But I have another question.
Yeah, I see Roy is.
Okay, so you can come back to me after.
Hi, hi Mattan.
Hi, Roy.
So my main question is, you mentioned, and there was some discussion about choosing your priors and how to determine them. But I was wondering, because you talked about choosing the rope, and I have an intuition that those two are somewhat related. So if they're not, I'd like to know why, because both of them seem to indicate some idea on what you'd expect as the result and so on. And if they are related, then like maybe specify a bit more how they are related. Like how would you choose your rope, taking into account your priors or in different ways?
Yeah, so I'm just going to bring us back to here. Those things can be related, right? So for example, what this prior is saying, it's actually cutting out the rope, right? I'm actually saying here, I have a prior expectation that my effect isn't some null-like effect. So I definitely can do that. I can specify a model that doesn't have the rope in its possibilities, and then talk about that. I've seen that happen less. The way I kind of combine those things is I'm saying my prior, let's say here, I'm saying what are the possible parameters of this effect, and then given that, what's the probability of this effect being interesting or having any practical implication? And then that is a question about the rope. But generally, I agree that right. But they're kind of a little bit different types of question. One is asking, what am I expecting to see? And another is saying, what is interesting to me? So those are slightly different questions. Does that answer your question?
I mean, sort of. So the question I'm wondering is like, so if I'm, so here how it is like in my mind. So if I'm expecting to see a certain result, right?
Mm-hmm.
And presumably, I usually expect results that are interesting. No one goes to do the research to get uninteresting results, right? So those two, in a sense, should be combined. So the question is like, am I making like basically one judgment call here, just about making the model of my prior, and then the rope is derived from that, or I'm making two decisions?
Well, you have to be careful not to fall into this, right? Not to have too strong priors, in which case your results, right, your posterior is known before you've collected any data whatsoever. So you do have to, I would say, on a philosophical sense, or even maybe a practical one, right? We're encountering reviewers. You do have to give yourself in your prior some room to be wrong. Okay, if you don't give yourself room to be wrong, you can't learn, right? This is maybe a tip for life. Allow yourself to be wrong, or you'll never learn anything. So maybe that's kind of how you can have those come together, right? If you just have if you just have two strong priors, if you're saying my effect, I'm expecting an interesting effect, so I'm going to only put priors on that, you have to give the rope some null values. You have to give it some place that it can like breathe and learn, essentially.
Okay, so you would say those are basically like two independent questions I have to ask myself, right? One, what's the prior, and then B, what's my rope?
Right.
Okay, so in that case, could you say a bit more on how would you determine the rope? Because you talked a bit about how one would determine the prior, but not how one would determine.
Well, let's take like the easiest case would be if we're looking at some treatment. Okay, I want to let's say have a vaccine for some virus. Let's say, I don't know if anyone's thinking about the same thing as I am, right? So my rope, my region of practical equivalence, something that a range that is non-interesting would be if the vaccine makes people sick, right? So any effect that actually worsens people's condition is not interesting to me, right? That may be interesting for like people who want to understand how the vaccine works, but for practical purposes, I'm not interested in that. Okay, so I would just define my rope as anything that is a negative outcome. And then we can get more specific, right? So I can say, you can define it like, let's say Cohen's D. Cohen defines a small effect size as a Cohen's D of 0.1. So let's say I'm like being conservative. I'm taking half of that. So that's like one way to define a rope. In Krushke's book, he does talk about how to define a rope. He does go into that a bit more. But you have to think what's practical, right? I will say that Bayesian statistics does, because we're not just trying to reject the null and see if our effect is just positive or if it's just negative, we do need to kind of think more about the actual scales of our parameters and not just kind of, see what happens kind of thing.
Okay.
Naomi, back to you.
Sorry, I have a question about power issues.
Yes. Oh boy. Yeah.
Yeah, sorry. It's just that we had a study just now where we had no control over sample size because it's a cohort study. And basically what happened with the and I think we're underpowered. And then we computed Bayesian factors as well as Fickreysionist statistics, thinking that if we're underpowered, Bayesian analysis would give us more information because we could support the null.
Mm-hmm.
I don't think
But
that was true. I think we just,
yeah.
everything we got was anecdotal in directions.
Right, so power works in both ways for Bayes factors. If you're underpowered, you're also underpowered to support the null, not just to reject it. For power considerations, just like basically anything that's more complex than like a multiple regression, for power analysis, you have to like do simulations. Like there's no way out of that. I will say that the advantage here is because we don't have a problem of or at least it's not as severe for controlling for error rates, we can do data peaking. We can keep collecting data until our results are conclusive, essentially.
Hey, Mattan, I have, oh, sorry, you have.
No, go ahead.
Okay, thank you. Mattan, thank you for this really great workshop.
Thank you.
Just wondering if I'm doing now a replication of my study, is there, or how do I use my posterior as the next prior for the next?
Oh, there's yeah. That's actually, if you're doing an exact replication,
yeah.
If you're doing an exact replication, what you can do is actually combine the data from both studies and compare it to the results that you saw only after the first study, right? Because and then in that way, the posterior actually becomes the new prior. If you email me later, I'll put back my contact stuff. I can send you a paper that discusses how to do that more specifically.
Thanks.
Yoav.
No, I just wanted to ask if there are more questions. So, yeah.
I have a question. It's not actually a question. It's more like a request. The link for the GitHub that you put in the presentation is not working.
No way.
So if you could upload a new one after the talk.
Yeah, I will. Which one?
The one in the beginning for the GitHub where you have the R code and.
Oh yeah. Okay, I'll fix that.
Okay, thank you.
Anyone else? Okay, so Mattan, thank you very much. It was really illuminating. I learned a lot. And yeah, thank you.
Thank you.
Okay. Hi. We will be resuming at 12 o'clock. And you can enter before. We will be opening about 10 minutes before 12 if you want to check your connection, etc. Okay? See you at 12 then. Bye-bye.
Mattan, one last question, please.
Yeah.
Okay.
Do you have like a recommendation, a book where you recommend how to learn to use Stan independently?
I've never had to do that, so so no.
Because Krushka's book is perfect for learning JAX, but if Stan is easier,
doesn't he also have in the second edition? Doesn't he also have Stan code?
I will check that. That is
Shachar, I think Shachar would know the answer to that. Oh.
Who's Shachar?
Shachar, open your mic.
Oh.
Hi, can you please repeat the question?
Doesn't Kushka's book in the second edition, he also has Stan code?
I think so.
Yeah, I also think so.
I'll check that.
Mattan?
Yes.
Hi, another question. I was wondering in regard to what you said to Roy, why not use always a flat and a wide prior?
Well, for practical purposes, let's say, I gave the example of using really complex models, right? So if I'm using a really, really complex model and I'm telling my model, search everywhere, my model will have a hard time finding kind of like the best parameters to describe my data, etc. So if I use more specific values, I can actually help my model reveal patterns in the data. Also, we usually want, it's not a bad thing to use flat priors. I'm not saying don't ever do that. I'm just saying that they're not objective. That's all I'm saying. We have to think like, what is, right? If I showed all the different pictures of the priors, we have to ask, what are we saying about what we know? And I think that I will say that I think in most cases, completely flat priors are unreasonable, right? We don't know nothing, right? I know, for example, that reaction times aren't going to be, right, 10 years, right? So it's not reasonable to say that an effect of 10 years in my reaction time is just as probable as an effect of half a second. That's not a reasonable statement.
Okay, cool, thanks.
Anyone else?
Yes, I have a small question also, Mattan. It's not only the JASP has Bayesian statistics, also SPSS recently added Bayesian statistics. What's about the prior there? It's different than in JASP, because if you do the same calculation in JASP and in SPSS, it doesn't give you the same answer.
Yeah, I don't know. I played around with that with they had like a beta like 4 years ago for SPSS, and I think that was the last time I opened SPSS, and I wasn't quite able to get that to work back then. So I don't know what they've changed from then to now. So I don't know. Sorry.
Okay, fair enough. Okay, so we'll resume at 10 minutes to 12. See you all.
Bye-bye.